Unit 7, Modern Physics, 7.1, Discrete Energy and Radioactivity. First thing we need to understand is that light carries energy, and we can find the amount of energy that light carries by the equation E equals hf, where h is going to be Planck's constant, which is a value here, 6.63 times 10 negative 34 joule seconds. So we can see that this is an incredibly small unit here, which means for the amount of energy that light carries based on the frequency, it's not going to be a lot, but it is something that we can measure. Now, what we understand is that the speed of light is the same for all forms of light. So whether it's anything in that electromagnetic spectrum travels at the speed of light, which is wavelength times frequency. This equation were provided in our physics data booklet, and I'm going to show us how we get the second equation, which is provided as well. If we were to solve for frequency, frequency then would be the speed of light divided by my wavelength. And what I'm going to do is I'm going to plug this equation into that one to then get the idea that E equals hc over wavelength. And the IB physics actually writes it in the form of wavelength equals hc over E. So in one method, we can find the quantity of energy based on the frequency. The other method, we can find the quantity of energy based on the wavelength. If we don't have the frequency, both of them get there just using different values. This one, though, is provided in the form of wavelength equals, but we can still do a little bit of algebra and solve for energy. Okay, so we're going to take this idea that light carries energy, and we're going to apply it to this phenomenon here, which is just the idea of atomic spectroscopy, which looks at the signature pretty much of different gases or different elements. And their signature is viewed in light. And we're going to try to understand that. So if we were to take a look at just plain white light and have it go through a diffraction gradient, we would get all the colors that we could see, all the way from ultraviolet to infrared. However, if we take that light and pass it through a certain element in a gas form, and then we looked at that light, we would get, again, we'd get that rainbow, but we'd have these blank spaces in these parts where there were actually no light that was being emitted. We could also then look at that light in a way where the emission spectrum would only show those individual beams of light that were actually missing up here. So a line spectrum is going to be discrete lines against a continuous background. So we see this continuous background of color, and there's these discrete points where no color actually is present. And we get this continuous background of black and these very discrete singular lines of color. And so the dark lines show energies that are going to be absorbed from the gas. So the light carrying energy passes through the gas. Some of that energy is absorbed, and that energy that is absorbed is going to be light energy that doesn't pass through, and it's going to be these black spaces. What can happen then is that gas can also emit light, and that's going to be these individual spectra here. And what you'll see is the same energies that that gas can absorb is going to be the same energies that that gas can release. So let's understand how this is happening and why this is happening. Okay, so why does this happen? If we take a look at an atom, so this is just going to be a very simple model of an atom. Here's our nucleus. Here's a single electron that's orbiting around this atom. It's going to be orbiting at what's called the ground state. So there's no excited aspect to this. It has no extra energy. It's just orbiting around that. Now, what we just showed was if we had some beam of light, which is going to shine at this atom, that light is a combination of all colors from red to purple. And most of that light is simply going to pass straight through. But every once in a while, you're going to get a beam of light that's going to come and it's going to hit this electron and it's going to excite it. It's going to cause it to jump up to an energy level. So this is the ground state. This is our first excited state, our first energy level. This is our second excited energy level. And there could be more outside of this. We're just going to focus on these: ground, first, and second. And so some photon comes and causes it to jump. Now, the concept of discrete is that this electron can only be at the ground, the first, or the second. It cannot be anywhere uh, in the middle. So it can't be anywhere here. It can't be anywhere there. It can only be on these very specific locations. So that's why we consider it as discrete. It has to be at those certain points. So that electron could be here at our ground state. It could be here at our first excited state. It could be here at our second excited state. And those different positions have different amounts of energy that is associated with them. Think about it in terms of potential energy. The ground state, the electron has the least potential energy. As it goes up, it has more potential energy. As it goes up, it has more potential energy. Well, for it to gain potential energy, something had to give it energy, and it's the light that actually gives that energy. So for the electron to jump from this ground state here to excited state 1, a certain amount of energy had to be given, right? So that's what these energy levels do. So if we went from 13.6 electron volts to 3.4 electron volts, that means I gained 10.2 electron volts of energy. And so, based on the concept that light carries energy in the form of H frequency, there is a single frequency of light which is going to carry that much energy. So let's say it's, this color of light. It's coming in, it's a combination. This color of light is a combination with all these other white light. It's going to come, it's going to hit this electron, and it's going to cause it to jump from this first energy level to the second. Now, if it went from this ground, from ground to my first energy level, if the electron didn't jump to the first energy level, but it skipped that one and went to the second level, that must have been something that provided enough energy to go from there to there. So that would be 13.6 to 1.51. That means it just gained 12.09 electron volts of energy. So that might be something of like a green light, where a very discrete frequency actually comes in and has the right amount of energy to cause it to jump. And so when these electrons absorb energy, they're going to jump to higher energy levels. Now, concept of energy is energy cannot be created or destroyed. It can just be transferred. So if we have that electron hanging out here in the second excited state, it's eventually going to come back down. Potential energy, right, turns into another form of energy. And that electron can take two pathways to get down. It can simply go straight back down this way. In that case, it would release 12.09 electron volts of energy in the form of light. Or it could take this path where it would go from excited state 2 to 1 and then back down there. And so this would be another amount of energy that it's releasing here. So we'd have one beam of light here, one beam of light there. So that's where we get, these are the absorption spectrum when they're absorbing energy and they're going from ground state to higher levels, right? And these are the emission spectrum when they're actually releasing light. So for electrons to go from higher energy level, they're going to be absorbing photons of light and energy. When they move back down, they're then going to be releasing some beam of light. And that's what we would get in our emission spectrum. So this concept of a photon of energy, right? A photon as photon energy, where a single particle of light is known as a photon. And that photon is carrying a very discrete amount of energy. Right? Each wavelength of light carries its own amount of energy, in the form of E equals HF. And those electrons are only jumping with very distinct amounts of energy. So a photon carries a certain amount of energy dependent upon its frequency, a discrete packet of light with discrete energy levels. It's not a range of energy, but it is a single amount of energy based on the frequency of light. Discrete meaning we must have a well-defined level with no intermediate levels. That's why those electrons don't jump wherever. They can only go from one level to the next with the very specific amounts of energy. So let's look at a question that might involve this concept. It says the emission spectrum of mercury has long been studied, and the visible spectrum is shown in figure 6a with some of the energy levels shown in 6b. Given these energy levels, what is the minimum and maximum energy of an emitted photon? So if we think about the maximum, right, if this is our ground state right here, the maximum emission, right, so remember emission is going down. Emission is where electrons are moving from higher energy levels down. So our maximum would be the biggest change here. So I would go from here to here, and that's how I would find my maximum amount of energy that is being emitted. So my max would simply be 10.44 minus 2.71, and that's going to equal 7.73 electron volts. Now my minimum then is I would need to find what's the smallest difference in this. And so if I look at this right here, these two are going to be the smallest. So if I had some electron that was here and it just bounced down to there, my minimum then would be 5.55, or yeah, we'll do 5.77 minus 10, oh, not 10, minus 5.55. And my minimum then would simply be 0.22 electron volts. And again, we could figure out, based on the concept of E equals HF, what frequency of light would produce both of these. This is the quantity of energy, 7.73, 0.22. Then what frequency of light corresponds to each one of those? And that's how I would then identify which one of these beams of light represents my maximum, which one represents my minimum. Now, some people might say, well, why isn't 10.44 my maximum? If I have an electron in my ground state and it gets 10.44 electron volts of energy, it's actually being ionized. Okay, so we lose that electron. So the highest form of energy, or the highest energy level it could have, is this 2.71. If there's an electron here, it only needs 2.71 electron volts to be ionized. But if it drops all the way back down here, it went from 2.71 to 10.44. The last part of the question says the wavelength of prominent green line is 546 nanometers. To what transition does that correspond? So what I can do is I can say, okay, well, that's my wavelength. So I'm going to use the HC over wavelength to figure out how much energy that is emitting. We're going to plug in Planck's constant, which is 6.63 times 10 to the negative 34, times the speed of light, which is 3 times 10 to the 8th, divided by that wavelength, which is 546 times 10 to the negative 9, negative 9 meters. With that, then, we're going to get the amount of energy that it would have. That energy would be 3.64 times 10 to the negative 19 joules. And then to find electron volts, we're going to divide that by 1.6 times 10 to the negative 19. And that's going to get me a value of 2.27, electron volts. So then I could say, okay, what level to level can I get to that to do 2.27? And I can see, okay, if I start here and I transition down to here, 2.71, 4.98, 2.27 electron volts difference. So that's the transition going from N6 to N4. And that's how I would figure out which wavelength of light that transition corresponds to. So we can make up from the time, right? Nuclear structure, we know inside the nucleus, right, are protons and neutrons. They have charge of +1 and 0, and they have mass essentially of both being equivalents, okay? They're not actually the same, but they're close enough that we can say their atomic mass unit is 1, okay? You see in your reference sheet on page 2, you see the electron rest mass, the proton rest mass, and the neutron rest mass. You also see the unified atomic mass units, okay? And that's how they are all related, okay? An electron is outside of a nucleus, obviously. It has a -1 charge, and it has a mass roughly 1 to the 1840. Okay. Now, when we look at elements, elements have two main numbers associated with them. If this is lithium, it has 7 and 3. 3 is the atomic number, and that tells me the number of protons. 7 is the atomic mass. That tells me the number of protons and neutrons, which are both called nucleons, just anything in the nucleus, okay? And so how many neutrons would this lithium have? It would have 4, 7 minus 3, right? That there are isotopes. Lithium 5, 7, and 9. You cannot cry about this. This is super easy, right? What is the difference between these 3 isotopes of lithium? Number of neutrons, okay? This lithium has 2, this lithium has 4, this lithium has, 6, okay? Neutrons act as glue in the nucleus, okay? There is something called the strong nuclear force. It is one of the 4 fundamental forces in physics. Every force is a component of strong nuclear force, weak nuclear force, electrostatics, or gravity. Right? Yes. Right? The strong nuclear force only acts inside the nucleus between protons and neutrons. It doesn't act anywhere else, right? Along with quarks. It only acts over very short distances, but it is strong. Why does this make sense? Inside a nucleus of lithium, we have how many protons? No. We have 3. And what do those protons, because they're all positive, want to do to each other? They want to push away from each other. But the neutrons act as glue in holding that nucleus together. The only element that doesn't have any neutrons is hydrogen. And that's because there's only 1 proton, so there's nothing else repelling it. Okay? Radioactivity is the process when we have emissions of ionizing radiation as a result of changes in nuclear energy of a nucleus, right? You guys understand this. You probably don't have to write this down, right? A radionuclide or a radioisotope is any nuclide that is unstable that goes through decay, right? So if it's not stable, it's a radionuclide or a radioisotope, okay? And we're going to say that because certain isotopes of certain elements are radioactive and certain isotopes are not, right? So certain isotopes will go through radioactivity, meaning their nucleus will break apart in some way. You've all learned alpha, beta, gamma decay, all right? And so we're going to identify those isotopes that go through that process. Everybody okay with this? Okay. All right. So here's what we need to understand, right? In physical science with me, we did this. We actually graphed this on Excel, and it was beautiful, right? But here's what we see. Down here is the number of protons. Right here's the number of neutrons. As we add protons, we change our elements, yes? Each element is identified by the number of protons that it has. So what we notice, this right here is a line that shows a ratio of 1 to 1, meaning 1 proton to 1 neutron. Okay, and what we notice is that the first 20 elements kind of follow along on that pattern. Pretty much 1 proton to 1 neutron, give or take, okay? But once we get greater than 20, we notice that all of our elements, the stable ones are in black, the unstable ones are yellow. All of our elements start to become more and more what? Neutrons, yes? Okay? Now, if there's that magic number of neutrons to protons, it's stable. But for the most part, most of our isotopes are unstable or radioactive. Yes? Okay? So there's a fine point where there are stable atoms, okay, but most of them are unstable. Everybody okay with that? Okay. Last part with this. Why does this start to become higher than this 1 to 1 line? Well, as I have more protons, there's more things that are repelling. Yes? So is it going to be harder or easier to keep that nucleus together? Harder. So I need more and more neutrons to hold that nucleus together. Yes? Okay? If I have 2, now if we think about this, Okay, a vertical line represents the same elements. Okay, so this purple line, I know it's not perfectly vertical, but we got to think about that vertical line is all the isotopes of that element. Notice there's a very small amount that are stable. Okay, if it's above, it's a certain type of radioactivity. If it's below, it's a certain type of radioactivity, and we'll go through that. Yes, but if we think about this, it's just if it's below, there's not enough neutrons to hold it together. So eventually, what will it do? It will break. So let's go through the main types of decay. Again, most of this should be reviewed from physical science at least, right? The first one is alpha particle or an alpha decay. Alpha decay is considered a helium nucleus, okay? And that helium typically has 2 protons and 2 neutrons, so it has an atomic mass of 4, whereas an alpha particle has that same result, okay? 2 protons, 4 nucleons, or 2 neutrons. All right, here's an example of alpha decay. We have uranium-92, 238. It spits out an alpha particle, yes? So how many protons are left? 90, which is now thorium, and we have now 234 nucleons left. Notice the left has to equal the right. We can handle that, yes? Also, sometimes there would be gamma decay that comes along with this, but gamma decay, right, has 0 and 0. So does that affect any of these numbers? No, gamma is light. It is just light with no protons and no mass. Yes? No charge, no mass. Beta decay. There are 2 types of beta decay. Did you guys learn about this in chemistry? No. Okay. Beta decay. We're going to go through beta minus. That is the one that we teach in physical science. Right? And beta minus. Inside of a nucleus, a neutron spontaneously turns into a proton and an electron. Okay? Now, this is okay because a neutron has what charge? And it turns into a proton and an electron, so the net charge of them is still, so our conservation of charge is still followed, yes? But a neutron transitions into a proton and an electron, okay? And we're going to write that as this. And then this is our beta particle, right? It is essentially an electron gets emitted from the nucleus, and an electron has a charge of -1. So that's kind of how we memorize that. An electron is -1. It's also going to shoot out something called an antineutrino. We're not going to worry about what that is right now, but it just emits that, which, again, just like a photon, does it have any mass or charge? No. All right? But an antineutrino is indicated by the line above this symbol. Okay, so a neutrino would just be the symbol. An antineutrino would be like the line. Okay, and logic systems, do you learn logics in computer programming? We do it in engineering. This is a common symbol for anti or not. All right, so not would be this line above it. Okay, here's what happens. A neutron, which has a charge of 0 and a mass of 1, turns into a proton, which has a mass of 1 and a charge of 1, and an electron, which has a mass of 0 and a charge of -1, yes? And an antineutrino. So does the left still equal the right? Yes. Okay, here's an example of this process happening. Thorium-234 loses this beta particle and an antineutrino. So it gained a proton. So we went from 90 to 91, yes? And our mass stays the same because a proton and a neutron have the same mass. Okay? Everybody okay with this? Okay, beta plus is just the opposite of beta minus. Beta plus, what do we have here? We have a proton which turns into a neutron and a positron. Okay? These are subatomic particles, okay? A positron is an electron, but with a positive charge, okay? So, and it also shoots out what's called an electron neutrino, which, notice, again, it's the same thing. It just doesn't have the line above it, okay? Neutron and a proton have the same mass, and nothing else over here has mass, okay? A proton and a positron have the same charge, and nothing over here has charge. So our charge and our mass are both conserved. Everybody okay with that? Okay, here's an example of this. Oxygen 15 goes through beta positive or beta plus, meaning it loses a proton, yes? Because it turned into a neutron. So we go from 8 protons to 7. Our nucleons stay the same. We gained in a neutron, but we lost a proton, so we still have 15 nucleons. All right? We lose a positron from the nucleus and an electron neutrino. Everybody okay with that? Could gamma decay go with this? Yes, we could add a gamma here if we wanted to. We could add gamma to anything. Okay? But again, that's 0, 0, so would that affect anything as well? No. Beta decay is relatively, well, I guess it's a little bit more dangerous. Alpha decay is the least dangerous. Beta decay is a little bit more dangerous.
Well, in terms of exposure.
Yes.
But like.
Okay, lastly, gamma decay. Gamma decay is a high energy photon emitted, 0, and I've gone through this a few times, 0, 0, gamma from an excited nucleus, okay? So it could be anything. This is anything on the electromagnetic spectrum. Okay? So in theory, could it be radio waves? Yes. Could it be microwaves? Yes. Are those dangerous? No. Could it be gamma and X-rays? Yes. Are those dangerous? Yes. Okay? Could it be light? Absolutely. Okay? Absolutely. That is pretty much all you're doing when you're in chemistry when you look through that too, okay? And has anyone not done that and not know what I'm talking about? Look through the like beams, like glass tubes of light, look through a little thing, you see the colors. Has anyone not done that? Okay, I'll see if I can get that down here for next week so you guys can see that, all right? Because it's kind of cool. The way we would draw this is thorium 23490. The result is thorium 23490, gamma, yes? The only difference is we have this asterisk, which that stands for my excited state. Okay?